So this is the Mathcad for the concrete combined retaining wall and boundary wall design. So this is subject not just to earth pressure, it's also subject to wind loading. So this was a real world example. This is one I did a couple of years ago on a real project. So it's a concrete retaining wall, rather high. So your retained height is 1100 and your boundary wall height is 1800. So you need to calculate what the wind load is as well as what the earth load is as well. So some basic parameters of the wall, some concrete wall material properties, the loading. We've assumed surcharge loading on the backfill is only 2 because there's no traffic in there, it's only people. And it obviously acts on the soil level. The design wind speed, because we're looking at an IL1 structure, we're looking at a return period of 1 in 100 years. So our design wind speed is 37, and that gives you dynamic wind pressure of 0.84. Because our pressure coefficients are 1.2, we're going to work out with a wind pressure of 1, or just slightly over 1 kPa. So our combination factors for live loading on the back of the wall will be 0.3 in this case. We've got strength reduction factors as we've seen before as 0.5. If you're looking at long-term and loading, you can look at reduction factors of 0.4 again for the line load as well as a surcharge load. Our soil pressure factor is going to be 1.5, but for earthquakes it will be 1. So our soil parameters are given here, very similar to the previous example. And we've worked out the active pressure and the passive pressure using the Coulomb equations. So they work as 0.3 and 6.1. So the seismic parameters, so we're looking at a relatively short return period. So we're looking at a topographic amplification of 1 and a wall displacement factor of 0.3. So our KH works out as a tiny 0.034 G. And that MO equation, as it's called, I've split it up into 2. So we've got this parameter D, which takes into account the parameter theta, which is looking at the horizontal acceleration due to the earthquake. And we shove that D into the denominator of the equation for active earth pressure, KAE, in the earthquake case. So here are the seismic parameters for the wall. So we're looking at a return period of 0.5. And near fault again as 1. So we're looking at ductility here as 1 and our period is 0.4. And therefore our seismic coefficient is a mere 0.21. So our wall loading, we work out long-term, short-term and earthquake loading. You're going to need to take account of the weight of the wall above the ground. So the weight of the wall actually imposes an earthquake load on your retaining wall now. So the seismic load of the wall, I know it's not a lot, but it counts. It's 1.36 kilonewtons per meter. We've got our wind load and we've got our long-term and short-term earthquake loads. So from that, we get our bending, so our moments. Looking at long term, you just take those forces that you've worked out above, some due to the soil, some due to the surcharge, and multiply it by the angle required, and you get a 1.78 kilonewton meters of moment. Looking at the short term, you've got slightly different parameters, and that works out as 2. Similarly with the earthquake, you're using the Ka for the earthquake with a factor and it works out as 1.31. We've also got the wind on the wall and the EQ of the wall. So our design moment is we take the maximums of these parameters for the cases that can coexist, in which case our design moment works out as 7.73 and our design shear works out as 9.7. So not all of the moments can exist at once. So we look at the stability of the footing. Again, working out what the dead load of the wall and the dead load of the footing. So these are going to be our restoring moments. What are our lever arms? And our total restoring moment works out as 16.2. The distance to the reaction works out as 0.41. That's merely the moment divided by the reaction. So our bearing length is 0.82. That gives us a bearing pressure of 25.12 kPa. So let's check the bearing capacity. And again, we're looking at soil parameters that we've seen before. We look at the effective stress at the foundation. That's a 5.1 because of the depth. We've got a bearing factor again taken from B1 VM4. So our NQ, NC, and N gamma are calculated. We've taken our shape factors all as 1 because we're looking at a long strip foundation in this case. We're looking at horizontal ground, so our ground inclination factors are 1. We've got depth factors calculated and our load inclination factors worked out from the loading above, which gives us an ultimate bearing strength of 234 and a design bearing strength is 117. So our bearing strength utilization is 21% based on that. So we're okay with that. Looking at the concrete footing, so we put in similar parameters from above. We've got our concrete strengths and we're working out the concrete footing sizes. So we've got a thickness of 300 and a width, looking at unit width and gross area of the concrete. Again, we're looking at HD12s, calling it vertical reinforcement. The vertical reinforcement continues down into the footing. And so we've got our steel areas calculated from that. And from that, using the equations in NZS 3101, we can work out what the moment capacity is. In this case, the moment capacity of the footing is 32.5. Yet the applied moment is 12, worked out from above. So our utilization is 37%. Again, looking at the shear capacity of the footing, we work out the concrete shear capacity is 0.44. And the shear resistance provided by the stirrups, in this case the bars, is 73, which gives us a shear capacity of 123 kilonewtons. And that gives us a utilization of 17%.